Hey, and welcome to this soldering stream. I'm waiting till the stream goes live to see everything works fine. And we'll just quickly test the audio to see. Yeah, that looks good. What am I doing today? I created this PCB and the second PCB as an addition to it. So it's one project, two PCBs. The story behind it is that the NRF 52840 and also the NRF 52832, that is a Nordic Semiconductor Bluetooth Low Energy chip, which is used in many smartwatches and many devices like tracker, location tracker, or the Apple AirTag, for example. And I'm playing around with them for a long time now. And as the producers do lock the content of the flash of some devices, or most devices these days, it is always a hassle to reverse engineer the pinout and to see how the firmware is handling all the hardware stuff to get your own custom firmware on a device like a smartwatch or so. I can show one here. So like this is the B5, for example, and it has luckily on the USB port, which can charge it, the data pins connected to the SWD interface. This interface is used to program the microcontroller, the NRF chip, without any other connections like serial or a parallel connection. And normally you would use such a flashing adapter, an ST-Link or an J-Link to flash a new firmware onto the devices. I did already show the project in an earlier video that I used an ESP32 to emulate the SWD protocol and to use it to read and write the flash content of the NRF chip. And the lock bit problem was luckily there was luckily a guy named Unlimited Resolution Solution. I need to look it up. So limited results. Now it's So the guy named Limited Results made a proof of concept of glitching the one power rail of the chip to a ground level, and that way it was possible to glitch the protection bit or the flash protection bit to read out the firmware. So here you can see I connected this little wire to one capacitor, which is then connected to this one power rail we need in the NRF. And if it's holds to ground, it will then try to glitch automatically the right moment. This is in the firmware I created inside of the ESP32 contained. So the ESP32 does read the SWD interface and looks if it's locked or not. And also the glitching is happening then on the ESP32 at the precise moment and with a very precise timing to get the read protection exploited. And so I used this breadboard a lot now, and every time it was pretty annoying as all the wires dangling here around and unplugging and such. And so I created now a PCB once, main PCB, I would say, where the ESP32 is laying and the MOSFETs and transistors to do the glitching and also to connect an oscilloscope simpler to it. And then some slave PCBs to connect your target to your device. So you have a few of the PCBs and can solder every PCB to one device you want to read out. And now let's check a bit the comments. Oh, there are a lot of people there. Hi Johnny. Hi Envy. Oh, nice to see you here. And Brian as well. So, and Abdullah as well. I hope everything works as intended. As shortly before the stream, I sadly realized that the ESP boards I have here are not working properly, as it seems like the voltage converter on it is not getting to deliver enough current. I quickly tried to solder a capacitor on there, but they go into brownout. Maybe we can solve it after soldering the PCBs. So, and I have to do the official stuff. This stream and video is sponsored by PCBWay. They kindly provided the PCBs for free. And I would use them anyway, as I have nice results from them. Okay, so let's unpack the PCBs. Maybe I make the image a bit bigger. However this works. So, Brian, I don't know what chip it is. It has a 4B2X on it, the voltage converter for the 3.0 volt. So we can now open up the PCBs to look what they do, how they look. And if they work. Let's first just look a bit at them. My plan was to have this master PCB like this, and here are 5 LEDs for status and the oscilloscope connection, also good reachable, and then the target PCB on top with some pin headers and connectors to get them nicely aligned, and you have a big place for the device like a smartwatch. Or in this case, we will use the NRF52840 demo board or dongle, which is a nice cheap dongle to test the NRF chip. One thing that's a bit unfortunate is we have to directly solder the ESP on the main board, as otherwise the pin headers are too too near. How do I say it? There is not enough room elsewise if it would be soldered on top of it. Okay, Brian, the upload works fine, but just after starting the program itself and it tries to enable the Wi-Fi, at that moment it starts to crash the ESP with the brownout reset. We can take a look at that later. So I do need to get some parts together still. I have some already prepared. This was everything very unplanned. So what I'm trying to do is to get a bit of solder paste everywhere with a toothpick as my soldering pistol unfortunately broke the last time. If I now try to push out the solder paste, it just retches, and it's very annoying to get it out. So as I don't have a stencil anyway, I was just gonna use that. And this solder paste does come right out of the refrigerator. It should be quite good, but I don't know. It's a new one. I just wanted to try if it's better to get a new solder paste than some old one I had laying around anyway for other projects, but this doesn't work so well. Maybe I should get the other stuff. Yeah, I need to get the top of it to get a thinner stripe out of it. I'm back in a moment. So these should work or be the right size, hopefully. Yeah, that looks good. So now I need to press a lot on the back to get it out without retching over. So we need the old stuff for now. So this PCB only has very few parts, so it should not be too bad, but this really does not work. So another way now would be to use this type, but I think this is a 3D printed one, and I used it before I had this pistol. But I think as I removed some parts of this syringe, that it does not work anymore. should work. Yeah. If this doesn't work as well, I will just solder it by hand. Yeah, but there's coming something out. That's good. So now to restart. Not the best solution. So this works better. So now I need to constantly screw a bit and still apply the right amount. It should not be too hard. So yeah, that works way better now. As you may can see, I switched to 0603 parts, as it's just way, yeah, more flexible in size if you have a really small device. So that should be it already. And we have for once a 5-volt switched rail and a 3.3 volts switched rail to, if needed, switch a 5-volt power supply on and off to the NRF. And in the old solution here, there was just an GPIO that was switched and which then powered the whole NRF and the whole device, which was not the best solution. So here I now created the switched voltage rails above or within a MOSFET. So okay, that's maybe better overall. So I now got a few parts already here. And a list of everything that's needed and needs to be placed onto it. Yeah, so I'm just starting with what I have here already. The 100 ohm resistor. which is, yeah, what is it? R10, it's here. And this should take a while. So then we have 1K. I'm just erasing it. There are a lot, 9 pieces. Now we should be back. There was something off. Need to get all the microphones muted again. And hopefully you can hear me now. I'll just quickly check it out. Yeah, that looks good. Excuse this disturbance. And hey, Dustin. So yeah, now every microphone should be muted except the one I'm wearing, as it has the best sound. So, and I hope the smartphone I'm using to record the PCB with or to film the PCB with is not overheating, as the battery symbol is blinking for some reason. So that is a minor problem maybe. So yeah, where was I? At the 1K resistors. So I'm just placing them where they are needed. And Unfortunately, the plier is too magnetic in its state to just drop the resistors if they are the wrong direction or the wrong orientation. Normally this helps a lot, but yeah, rotating them is okay as well. So that were all the 1K resistors. So I can also do a line above it. Then we have one 10K resistor. If I get that open. Yeah. So after I disconnected the power supply from the smartphone, the battery icon isn't blinking anymore. So I guess it was just too much charging and using the camera for so long. So we have the 10K resistor here. And now I need to get the transistor and the MOSFET. For once, here are two P-channel MOSFETs and here are two NPN transistors. Maybe I just should get them. I will try it out. So I have the big box of parts here that needs to be searched. And what do we need? Okay. It looks like the camera did go off for a moment. But should be back now. Yeah. I need to plan this a bit more ahead in the future. Hey Moham. Greetings back. So I'm just looking up what exact part number the transistor has. I'm looking for 36431. Okay. Yeah, it could really be planned better. Especially as I need the other parts as well in the moment. No luck there. But we have another big box of parts where we can look at. Here we go. One part. We will search for the other ones in a moment. So these are NPN transistors. Yeah. And we need 2 of them. These are used as a driver for the 3.3 and 5 volt rail MOSFET, as only the 3.3 volt rail would have worked anyway by testing it. So I'm just placing them here. Like this. So, and now I'm searching for the C118153. What a coincidence. Here they are. There as well 2 pieces. So I'm really impressed these days by how much such MOSFETs can switch these small SOT 323, I think, or SC59 MOSFETs can switch just 3 ampere at 16 volt maximum, which is a lot in my eyes. So, and for the last part, I'm only having the big MOSFET I created here on the PCB. So I will remove it from one of the breadboard boards, like here, and use it from there. The other part is still being shipped to me. So I will just get another one from them. I got now one module here, which I already salvaged and removed one of it. And I'm just thinking right now how to remove it. Maybe I should try it with the heat plate. It's a bit hard to get it flat on it, as the pins from the connector and the other one as well are in the way. So I may just desolder it by hand with the pine soldering iron. So I have used the shortest cable for whatever reason. So I'm just using another one, which does not work. Okay. But then we can go and can get Brian Lux Flexi Friend, which does also work on the pine soldering iron with that specific power supply. So shout out to Brian. Now the soldering iron also works on most other USB-C power supplies. So to remove it, I first heat the small legs a bit up, and then the big one in the middle, which needs the most heat. And I'm just, putting a lot of solder on it until it is soldered. And I'm also increasing the temperature of the soldering iron to get quicker to this state. So, and then reheating the legs again, and now it's apart. I'm turning off the soldering iron for now. And what I totally missed is the LED part. And we now still need to select which one to use. So I would use white LEDs for the power rail, just as a good indicator. So I need 2 of them. And here I'm always needing to check the orientation, as I would get it wrong elsewhere. So we have here another of these modules, and there we can see the green part is at the ground plane. So better check before placing it wrong. So now I also quickly check where the ground plane is on the PCB. So it is the little cut edge is ground for this one. So I'm just placing the 2 LEDs at that orientation, so they should work. So, and for the other 3 LEDs, I would just simply use RGB, so red, green, and blue, which should fit the most. Like this, and we start with red. So here again, the green part to the negative side. Then we got a blue LED inside of it. And we're placing it to the last position. And then the last green one. Here, if I can get it open. So now. Like so. And now I would start to preheat the heat plate. It's a fairly nice device, which does not work for some reason. Let's see. Whatever this was. So I printed from Timon this frame to support some longer PCBs, which is quite nice, as if you have such a PCB, it's okay in the middle, but if you go to the corner, it would just drop, and that way it's nicely supported from it. So I'm just waiting till the heat is there. Don't know what this warning sign is. Ah, I'm now knowing it. It has an accelerometer sensor inside. So if I'm picking it up, it says it's not secure to heat. Yeah, okay. That makes sense. So I will put a bit more solder on it where the N-channel MOSFET comes, just to place it on it as well without problems. In the hope everything reflows as intended. And I'm just placing it already. So on some places I may have put too much solder paste on, but let's just see. You can see how quickly it does solder it. And also this solder paste is just floating everywhere, which is the reason I bought the other one, but that hadn't worked today. This is a 1.6 millimeter PCB, and on such a PCB, this is here 0.8 millimeter. The reflow is really happening very fast at 3 seconds or so. Now we can see it slowly getting reflowed. Yeah, that doesn't work too well. As there is too much solder on the pads, it seems the LEDs don't want to stick too well to it anymore. So maybe I resolder them by hand. Especially on these few parts, it's way simpler. Still to code. Yeah, so I'm just waiting a bit longer. Yeah, the LEDs just don't want to stick too well to the board. That's a bit unfortunate. Hey, Joven. So yeah, not too happy with that reflowing. It may be because of the thick board or because of too much solder, but we would use it anyway for now. Even if it does not look too nice, it still should work. Yeah, that's... Yeah, not too happy about it. Okay. Better next time. So hopefully this reflow does work. And yeah, it looks like it. It works fine. And I can really feel the whole PCB heating up a lot because of the ground plane everywhere. So it's not too nice to touch anymore. Yeah, that looks good. Should be cleanable. Yeah, also a bit too much. So, but yeah, that's really not nice. Not happy about it. A bit can be removed. So definitely it would be better to have the right amount of solder paste. Okay, but still. So we can get it off there again. Turn off the heat plate. So just checking. So yeah, I'm back again. So where do we go now? Hopefully the PCB is a bit cooled down now to touch it again. And yeah, you can clearly see some heat. Yeah, how do I call it? Some decoloring. So it's a bit dark here. And yeah, now some pin headers can be soldered on. For the oscilloscope one, I am using these yellow ones just for whatever reasons. Maybe I should cut them different. So like this. And I should preheat the soldering iron already, if I can find it. Here. For now, I may should just increase the height of the pin headers, even if it isn't that stable in that configuration, but then I can also put the ESP on with some pin headers. That way I can remove it, especially as the problems occurred just now, that it won't run as it should. So I got a few of these extra long feet types, and I'm going to place them here as high up as possible. So then the ESP should fit under it. Hopefully. And for the PCB, I'm using these here for the ESP to get the right distance. And in theory, it should be possible to only solder on the internal connectors, as the whole PCB is made to also be used by an ESP8266. So we can just plug this one in or the ESP32. And the pins are selected to be compatible with both chips. Only the firmware needs to be changed to the ESP8266 as well. Okay, so I'm just plugging it in or sticking it through and solder some headers. The rotation is now a bit off. Normally this is not too interesting, but I will just rotate them as well. Just so it looks at least a bit better. And we should prevent any burning from the paper by removing it. So I hope you are all there, because I cannot see any chat messages appearing. Is the stream working fine? So, oh, sorry, a bit out of image, out of frame. So this is really nothing to solder a lot from. There must be a better solution than this to connect the oscilloscope probes. I made it so we have two grounds, and one for the glitch and one for trigger. So it's possible to set the trigger on the oscilloscope so it will recognize the glitch, and then will show the time after it to have a better overview and a fixed position. So I'm now also cutting the pin header for the ESP board. There I will solder every pin, as it could be used on different boards. Like this. So I may refresh the chat quickly. Yeah, like that. And one more. And maybe the soldering iron could be left at a bit lower temperature again. So for that, well, we can already also cut them for the top board. And there I will be using the yellow one again, as it fits so well to the PCB. And yeah, just two of each for now. The connection is just mirrored, so the left side and right side has both the same connection, and I'm really hoping that it's not going to get any interference, so that the signal is still okay, even if it's split up at so many places. which would be not so great. Yeah, so I'm soldering the first connector in. Okay, I can really feel how less heat from the soldering iron is coming. How long it takes to solder it. So, first one in. So, and what I'm doing is always seeing if the connector is aligned correctly. I first solder in or solder one pin, look if it's at the right angle, and if not, I reheat it a bit so it can be at a 90-degree angle like that. So I did set the soldering iron temperature up again, and it's way simpler to solder it that way. This one here is a good investment. It's a metal sponge, I would call it. Oops. And it cleans the soldering iron quite well and does not need any water like the old one, the normal sponge version. So again, I'm looking for the right angle, and that looks good. So we now can also solder the other side, I guess. Here I will be using the pre-cut one from the ESP board with which it is delivered. Yeah, but I will solder on all four just as it looks better, even if it's not needed. So like this, and we can also plug in the other side already for the ESP. And that way we have it completely aligned. And I quickly check if this solution is really working. Yeah, but it looks good. The space should be enough between it. This is just the first test. So yeah, I'm now going to solder the ESP. It will take a while for the whole pin rows. Especially the inner row is a bit harder to get onto. And if such a bridge is there, we can for once just put even more solder on it and heat it up so it will drop automatically to the floor. And that way we can remove such a solder bridge. this is more of a tedious work now. And to the brownout detection problem I talked about earlier. So this ESP32 board has a problem, or I got 10 pieces of them and all have the same problem, which is that if the code is started, the ESP reboots with a brownout detection. And this seems to be a problem of the voltage regulator on here, which is there, that it cannot deliver enough current for the ESP with Wi-Fi turned on. And yeah, we need to look into that in a moment. That's also the reason for the pin header now, to still be able to replace it with a better board or a different one, which may work better. So on the bottom, I'm as well soldering all pins. Like this. Maybe I should rotate it for the other row. Yeah, that should be simple. So what are you all up to today on this lovely Monday? I had some dirty work to do while installing some wires in the wall for a customer. Which is very, more or less annoying work to do on a Monday. So to solder the extra long headers, I may just plug them in here, of course cut to the right length, and then put the board in. So this way, maybe a bit nicer cut. And here's this second one, can now not be used for the 6-pin version, but I'm using it for this side then. So one left. Here's one cut to less. So like this. And hopefully this does fit fine as well. So that should, yeah, that looks very good. Even if it's designed on two separate files, it does perfectly fit. So now I would first solder the corners in at a nice height, and then the rest. So it's simpler to hold it at position like this. Yeah, the rest should be fairly simple to solder now. Yeah, so that should be it. We can now pull it out and also pull out the ESP. And as the pin header is now so long, every little push can bend it, which is not the correct solution. But if this would be on the bottom, we could solder them directly at the bottom as well. So now the plan is, if I can get back the NRF board, here it is. So now the plan is to have it laying here or any other NRF device, use some tin copper wires, some thin tinned copper wires like this. This is a 0.2 millimeter one. And we can then solder onto the pin, the needed one, and onto the device. And that way we have it nicely placed here. Can connect the oscilloscope to these two ports. And just do the rest at the interface, the website. And so I will now connect up the NRF. So we can get it out. We can test the main board later as well. So like this, we got the glitch output of the DEC 4 or 1 power rail. I have it linked in the GitHub description. Now it is swinging so much. So, and these tinned wires are very useful for a lot of stuff. So we have this very thin copper wire, and to get the tinned parts away, we can just reheat it with a soldering iron, and that way we have the very end tinned or solder able, and we can directly solder it to any solder without much trouble. So the NRF board has the pins nicely labeled. This is now SWDEO, so it's the in-out if it would stick to it. This is the data port of the SWD interface, and the other one is the clock part, which is the SW clock or SWC in my case. I'm just pre-tinning a bit there. So we have here the SWD connection. Then we need another wire for the clock signal. And one thing to change maybe is to place some double-sided tape on the PCB, so the target board does not dangle around a lot like here. And yeah, so as you can see, it's flapping in the breeze. For that reason, I'm going to solder the ground wire to the other side. So, and it's very strange that the chat is so silent. I'm just going to write something. So if you can write back or read it or hear it, please just make a small chat message. So yeah, the ground wire is now also on. And now I need to search for the 3.3 volt rail, which I may need to look up, but normally it also should be mentioned here. So we have voltage USB, we have VDD out. This should be the correct one. So the NRF 52840 has an internal voltage regulator from 5 volt to 3.3 or to 1.8 volts. So if it is used like this, like a USB device, it don't need any external voltage regulator. It can just be used like that. By default, if the flash is empty, the output of this voltage regulator is at 1.8 volts to not destroy any devices that come with a blank chip and are 1.8 volt devices. So it needs to be flashed to 3.3 volts. So in theory, this should be it in terms of connections. Now only the ESP must work, and I will just connect it to the board. Maybe I should remove the main board, the target board first, for obvious reasons. So we have one LED lighting up a bit. Not better to see. It seems like the one LED is driven. So what I will do now is see at the terminal monitor. And we'll also try to share the screen. Like this. And yeah, maybe a little bit bigger text. If it works. Yeah, that should be better. Okay. Thanks for your chat message. Crosaurus from Belgium. Belgia. So as we can see here now, we got the problem that the ESP is constantly rebooting. So if we scroll to the bottom, we see it flickering, which is not good. And if I do a re-upload now, I'm just seeing I'm uploading the wrong code. So it could be, okay, this wrong code does also use the I2C interface, and maybe this does interrupt anything. Let's see if the other code works fine. So now we can see it rebooting again. And I just need to see what we want. It's this code. And yeah, it's just getting all the files together. I need to change the pin out a bit for it to work, as this was just for the breadboard version. So now we can see it says welcome to ATC car, which is just the complete wrong code. And it seemed to have boot. Okay, so I will now boot the correct, or build the correct code. See if it works. In the meantime, I will just look up the correct pin out I used. And I should have printed it out. I will get it quickly. So here I'm back again. And I'm just seeing my father is visiting us. Hi, Arne. So we have the pin out now in this on this printed paper. It's, I bet, barely readable, but I will just copy it into the code. That's the simplest solution. In the hope, like this. So we have in the breadboard version only the one LED, which is the LED on the board, normally on the development board. And what we need to define is the glitcher output, which would be 23 in this case. The output for the voltage rail, I will just fix it to the 3.3 voltage rail for now, which is then 19. The oscilloscope pin is a pin which is an input, which then can be used to use the ESP32 as an oscilloscope itself, it does work to show where the correct position is, the correct voltage drop space, but it's not simple to use. It's still a brute force method to use it then. So I will look this pin up in a moment, as it's not mentioned here. So we need the SWD pin, which is the pin here. Data pin, it's 22, and the other one is 21, which fits well. And this should be it. Only that pin I need to look up for a moment. So it is only the SVP pin from the pinout itself, and is called GPIO 36. So this should be it. We'll just simply re-upload it, and maybe not, maybe I'll look the LED up. It's already 8 days ago, so I do not have it in mind anymore. There, it's not connected. Okay, so I will use pin 16 as the first LED for now. So it's now booted, and let's see what the serial monitor says. And yeah, it seems to boot successfully. It's nice. Okay, as we can already see here, it tried to read the SWD ID, which is not so important right now. Yeah, that I wanted to re-upload it once. Okay, of course, because the NRF is not connected, it cannot find the correct one. Let's see if we can get the other image bigger. So it seems like the voltage dropout or the brownout protection dropout was not the problem of the LDO, but just the wrong code. So we can now see the red LED turned on. If I can get somehow the screen a bit bigger again. Yeah, like this. So we have here now the 3.3 volt rail is lighting up, the red LED is lighting up, and the green LED is shining a bit. And I think it's because this pin is now undefined and in an unknown state. So I would need to get it like this, and just for testing, I will set these pins to output and high or low. So the LED is 6. And the other one is pin 5. And one should be left. No, nothing left. Okay. So, and then go for now. So if I now re-upload it, it should turn off these LEDs and only light up the red one. And yeah, maybe in the meantime, I also should measure the output of the voltage rail. If it works as expected, after the upload is done, I will quickly get the other. Somehow that doesn't work. Maybe like that. So we can now see the green LED turned off. That way, yeah, it's better. So blue and green is off, and only red is shining, and this 3.3 volt rail LED is on. And I will now measure the switched output of the 3.3 volt rail. And yeah, you cannot see it, but I. So yeah, still out of frame. It's not so important, I think. So yeah, we have the 3.3 volt output. And now the smartphone didn't want to work anymore. Yeah, so the phone is now too hot. I will just try to continue without that camera. I got one left to use. It's not the perfect one. Hopefully this works without rebooting anything. It does not look like this. No, sadly not for now, but no problem. We can get it to work anyway. We will continue this way. So you saw the main thing working. And if I now press the reset button, you can see that the 3.3 volt rail is turning off. And also you can see in the log messages on the PC that something is happening. And if I now plug in the NRF board itself, the target, and reset the ESP again, we should be able to see a different SWD detected. And I will just make this screen big. And yeah, we can see the 2BA01477. This is the SWD ID for the core, which is a Core M4, I think. Yeah, I'm not too sure about it. And we can also see already that it has detected the flash size. So this means that the board is unlocked. The next thing is now to open up the browser and go to the web server which this ESP board does create to control everything. I quickly need to see what I need to do for it without exposing anything wrong. So let me just look what is needed. Okay, so the ESP does connect already to a different Wi-Fi, which is not the one I want to go. So I think I need to reconnect the laptop as well to the other Wi-Fi. I will be back in a short moment. So, and if everything worked fine, we are back again in the correct web. Yeah, that looks good. Okay, so now we can see. No, you don't can see it. So I will be there in a moment. I just need to get the correct files for the FWD part, for the ESP part, like this. And then I will quickly share the screen again. Yeah, and that way. Add to stream. Yeah, that looks good. Okay, so we now got the ESP website, which we can reach by entering swd.local, which will get you this message, because we first need to upload an HTML file, or an HTM file in this case, which then the ESP can supply instead of this error message. The login data for the /edit, which you do need a lot later, is admin by default. And now we can see here a nice editor, which normally looks a bit better formatted. I will now open the correct file, which is this one, the index.htm, which is under the data folder in the GitHub repository linked, and we'll upload this one. So we can now see we have an index.html uploaded. If we now go back again to swd.local, we can see that a different website is greeting us, like so. And now we can scroll a bit to the bottom, where we can see the first info messages appearing, and we can see this little icon is flashing every second. This is meant to notify about the ESP running and the connection is steady. And to look if the ESP is connected correctly to the NRF, we can just re-click the init WSWD. It will just rerun the initializing and read out the content of the NRF. And if we would now set the lock bit of the NRF, we would, just for test, lock the NRF so it cannot be read anymore. But what I will do first is I will write some random numbers to the address location 0. This is needed because the NRF cannot be glitched without any content of it on it. So it will just simply not work. I tried it so long on a cleared NRF, it failed so often until I realized I have to put anything or something on the NRF. So I will click on write NRF flash, and this message shows, okay, it did write it, and we can now also read that register. So if I erase that value again and I click on read, it will show here that at address 0 the value is X and so on, whatever. So we can see that writing the memory of the NRF does work, and it's hard to show that it is really on the NRF. I lost the blink example I had earlier. So if I now set the lock bit of the NRF, the NRF is now locked and cannot be read anymore. If I now try to read again a value like so, you can see that it cannot read it as it is locked. So if I now retry to initialize the SWD interface, it can read the core. This is because the DAP interface is working still. This is meant to also unlock the NRF in terms you would want to reflash a locked NRF. So that interface is still working, and we can see we have correctly connected the NRF. What we now want to do is to glitch the NRF to read out the content, even if this lock bit is set the app protect bit. So I have this ESP32 side glitch oscilloscopes, and if I click on it, we can see here a nice graph of the analog input of the glitched voltage rail. And I hope it works. I never tested this PCB, but if I look at the board, we can see it is turning off the 3.3 volt rail as intended. And normally this should look a little bit better, different. So I'm not too confident right now that it is working like it should. But we can see that first the voltage is very high. So this is just the analog input in a timed graph. And we can see that the glitching here is happening. So if I increase the delay of the glitch moment, we see that the glitch is happening at a later point or at an earlier stage. And see here a little drop in the voltage history, and this should be the position where the glitch must happen. So I would now get out the real oscilloscope, as it's simpler and easier to see, and can then also be automated to do the glitching. We could now type, for example, 3000 and see it is at the right position where the glitch should happen. We can remember this 3000, can put it in the top, can set the glitch delay, and can then enable the glitching. So if I do this now, we see for once the board is crazy blinking. This is because it tries every seconds a few, maybe 20 or 30 tries in a second to find the right spot. And if we now also go a bit deeper, we can see here it tries different delays and different width of this, of the voltage drop itself. This now cannot be seen in the oscilloscope on the ESP, as it would just take too much time to transfer everything. And I am just going to look if maybe I did download an older version. Yeah, that looks so. It could be that I can re-upload another index.html file because some parts were missing. And I will just look if they are in the new version. So I will shortly disable the screen share and search for the new version. So I need to go back to the swd.local/edit and there go into the folder of the GitHub repo to to get the new version. And yeah, as it seems, it is correct. It was just an older version on my computer. So, and also I need, of course, to re-upload the newer code, which then has a bit more functions. So I can just get it back again and refresh it. And we can now see that we have more input fields here, which yeah, I just need to wait till the upload is done of the new code, of the new version. But I will quickly get the oscilloscope. So, and with any luck, the smartphone should be able to be used again. Blech. So, just starting up the oscilloscope, opening up the browser again. And we can add the oscilloscope to the screen. Okay, that looks good. So we have here the oscilloscope, we have the PCB again, and now two channels will be connected, one to the glitch side, in this case channel 2, and the other to the trigger side to see when the glitching is happening, like this. And we just need to configure the oscilloscope to it. I will just start the glitcher to get a better feeling for what is happening on the board. So there we can see a bit already what is happening, and I will now put the trigger of the view to the first channel, so the oscilloscope output status, and should change it to that for whatever reason, like this. Yeah, so that looks better now. We can then scale it a bit. This is now the top side is the trigger output, or the trigger for the oscilloscope, and the bottom part is the voltage rail of the DEC1 voltage. Yeah, and it is about 1.2 volts and will be a different voltage at some level or at some point. I think it's here. It's very hard to tell. It's not the correct output I'm expecting.
So something is definitely not working right. What I will do now is to go onto the 3.0 volt rail to see if this switches as expected or if it's always on or so. But we can see it does work. Maybe we should use a bigger delay. So the power of delay in this case, I will just set it to 500. That way the device will be off for longer, as we can see here now. And then I'm getting back to the glitch output. But it still looks to me like this is round about the correct area where we want to be, but normally it's way more clearer. So something is definitely strange or off. But let's see how it goes. We can go, and also normally we would have some big spike somewhere into the ground level of the glitch output. So if I use a different delay time, as we saw now, the delay is there. Now is debugging time. So we have the glitch output. Let me just check the schematics. So we have the glitch out here, that glitch out, and that glitch out. Glitch out in is 23. Maybe that is wrong, yeah, but that is correct. So the output is set like it should. The 3.2 volt rail is switched correctly. What I could now look for is if the input of the MOSFET for the glitching is switched correctly. To do so, I will use just the bare plug and look up what the 100 ohm resistor is, which is the R10. So that does not look so good. Again, we can see the spike, which we would look for. But it should go, it should look a lot different like this. So let's just recheck. Maybe a very simple blink example is a different way of checking it, or just unplugging the board itself to see what is going on. If it looks different then, but we can still see only this small, very light diffraction, which should go to ground level and not to a higher voltage.
So yeah, Christian, the
Schematic is really small and it's barely readable for myself. It was maybe not the best decision to just print it out. I will try to get it on the PC. Yeah, so that should work way better. So here we got the design file and also the schematic. It's as well not too big now, of course, but for example, the glitcher part should be simpler to read. So we have the glitch out I, which is coming from here. It's the GPIO 23 of the ESP32. It goes into the 100 ohm resistor and then in the 10K resistor, and is then going to only one populated N-channel MOSFET, and then to the glitch out part, which is for one the analog in, and second to the let's just see here, to the connectors to the second PCB, and also to the here to the oscilloscope, to the glitch output. And it's now just a question if anything in the glitch schematic is wrong or different than it should be. So this part, we can just look up the data sheet for it, hopefully. And yeah, it needs to be the correct one, the correct pin out. And it's also that part I'm using here. Just recheck it. PR7U. Okay, it's not the correct part or the same part. Maybe I should look it up then. So there we have the grade. Excuse me. We have the gate, the drain, the source on both parts at the correct location. So that should be good by comparing them to each other.
what I will do now is to
look a bit again to the schematic and compare the pins used at the module just for completion, yeah, just for checking it. So then we have 01A and 01C, which should be the 110
kilo ohm resistor. So if we Google that, it's, yeah. Yeah. So like this. We have the 01A, is the 100 ohm resistor,
which is directly connected to the input, the switched input. Then it is, we're at a resistor ladder. So it is connected to the
not simple, to the gate. Yeah, of course, to the gate. Yeah, to the gate. That's correct so far.
and then the other side, the 10K, the 01C.
It's here. It's 10 kilo ohm resistor is connected to here to ground, and there to the input signal.
Yeah, and if we look at the bottom, it is directly connected to ground. So that should be all right. The output is the big part.
And also correct. Yeah, this is also connected. So no missing connection there. This is the input
And this is ground. So this should be all right. Now it can only be that my bad
soldering practice here did
made it some shorts. Maybe I should resolder it or clean it a bit.
With
Yeah, I definitely should resolder it for once,
just to see what will change. So I need to connect the soldering iron again here. And I need to hurry up a bit as the battery is going low again. Just search for the plier.
So that's one resoldered. And the second resistor as well, which in theory shouldn't change much. So bit of new solder. Here. And also just reflowing the main MOSFET once for good matter. Okay, let's see if something changed. Yeah, reconnecting power. Status, and now I have to start the glitching, of course, which is now. A different thing could also be that the connection is not fully on the second port, as this 0402 capacitor is really small. But let's just plug it back in again. So if we now look at the oscilloscope, we can clearly see some rising here, which should be the voltage from that power rail, but that is definitely not right. I will try to disconnect the glitch. No. What could it be? If you've got any idea. So what we want to see here is 1 voltage. So like this, we would want a rising in the voltage to about here, or if we zoom it like that, a real voltage increasing like so, and then about here it should drop a little bit, and then it would continue. So this means the problem is that the DEC1 pin is not connected correctly. So it's not the glitcher that is wrong, as it seems, but the NRF side maybe. So maybe that should be reflowed once, to look out for that. So what we could do is just disconnecting it completely for now. And now measuring directly at the DEC1 output. Yeah, but as we can see, it's not rising. Now it must be rising. Except the 3.3 volt rail is not the correct input. I will just check that shortly. If the NRF dongle is maybe at the wrong pin.
Okay, so this is definitely a different one. Yeah, what we could test as well is just using the VUSB input just to test it. Yeah, but it must be the correct pin.
Yeah, so ground it correctly. Yeah, I will just try that. I will connect the VUSB to the 5-volt switched output and then look what is happening. Or what I will try first is to connect the 3.3 volt rail directly to a 3.3 volt power place. And also maybe just checking if I turn off the power or turn on the power of the NRF, if it starts to work or wants to work. Just need to so now it's correctly booted again. The glitcher is disabled, and if I disable the power supply, you can see the 3.3 volt rail just dropping or increasing as intended. And also the LED on the board is turning on and off, as you can see that way. And while the power is on, this part should increase by a lot. So there's really something off. I will check by directly connecting to the pin. And maybe I will also just get a different board. But first, the test. Of directly supplying 5 volts wherever I get this now. Or 3.3 volt. First, the switched 5 volts rail. This will take a short amount. I forgot to plug in the flexi thread. So I'm directly connecting it now to the V bus in, and we'll just see what is happening. But still, we can see that the second channel is too low for what it should be. So I'm also going to resolder it to 5 volts, which is then here at that place. Like so. Now the ESP is of course not correctly programmed, as we now need to switch it to the 5-volt pin. For that I'm just going to set the NRF power to the pin 19 and upload that again. We can now see it starts the upload. Maybe a better way to test it is to put a real firmware onto the dongle. As we saw, the SWD interface is perfectly running fine. It should be no problem. Okay, we still see the 3.3 volt rail only lighting up. I can just check if this is the right file. So the NRF power. Okay. Maybe I should change it to the correct pin. It was 18 and not 19. Quickly missed. Okay, so now hopefully the smartphone will continue to work, as it's only at 13% now. And yeah, just to have a better view of the LEDs. Yeah, we can now see the 5-volt rail LED lighting up as it should. And also here we can see the status of C is just checking it. Where do I put it? Did I put it? To the blue LED. It's unfortunately. Why did I do it? Okay. IO 16. 16. Yeah, okay. It's just not the blue LED in this case. It's the red LED. So the status OSCI is the red LED and is high now, of course. And if I connect the second channel to the switched 5-volt output, we should see that working. But we don't. Oh no. Okay. This small switch here on the oscilloscope probe was in the middle position. That's very unfortunate. So now we are speaking. Oh no. So, okay, here we have the 1-volt rail we wanted earlier. Damn it. I will just quickly reconnect the glitch output to the correct pin. And we'll also open up the web interface just to see what happens now if I enable the glitcher. So yeah, that looks way better now. We have a fully ground moment, and there we have a very nice signal. Okay, I will just quickly solder it on it again. Maybe we can get it to work. So just waiting to heat up again. Connecting it to the glitch output. Like so. And yeah, reconnecting the smartphone quickly to maybe get it to run a bit longer. So and now it does more than before, hopefully. So the NRF is connected. Nope, that still does not look right. So something is pulling down the second channel. Maybe it's incorrect again. But no. Yeah, that's definitely wrong. It should be the 1 volt from earlier that I showed. Like here, but it's still not there. So it could be the MOSFET that is maybe blown. I will desolder it to see what is happening then. To do this, I will now take the other power supply so the smartphone can still be charged. So yeah, maybe a bit more heat. Yes. It's a bit harder. Yeah, like this. Then I will power it on and see how the voltage levels do look like. And we'll most likely replace it then with a different one to see if it works better. So just simply reconnecting everything like so. Reconnecting the NRF. Like so. Maybe just checking. That's still wrong. Still not the signal I am looking for. So just checking out everything else that could have happened. Just quickly resoldering these. Pins. But it would be strange if this has any impact. So second channel is now floating, as we can see, as it should be this pin here now, and you can clearly see it going crazy when I touch it. The same should also be happening here and here. So that is the correct way now. What I will do now is also connect to the input pin of the MOSFET and see if that gets the right signal. Yeah, and there you can clearly see it. If I have the right mode, you can clearly see here this big spike where the input to the MOSFET is like it should. Then I will now also connect the NRF board again and see what the voltage level is doing there. Like so, but it's still at 0. But it also feels like the NRF does not get the correct power, even if I can initialize it. So I turn it off, turn it on. I initialize the SWD interface. Okay, now it says it's not connected. So I will switch back to the 3.3 volt rail, as this was not the culprit. For that, I'm just desoldering it here. And connecting it here again. And also, of course, the VDD out pin again. Like so. And now we can see if everything else happens now. But it does not look like it. It's still the second channel at a very low voltage point, which is just simply wrong. If I now disconnect it here and desolder it here and connect directly to it. And now it's definitely wrong. We had it once. So this sounds to me really like something with the power supply. The switch power supply is just not working like it should. Or maybe the ground is not fully connected or so. That should be the case. Just measuring it. Oops. So okay. That doesn't look good. That should be 3.3 volt. Yeah, I know what the reason is. As we reset the pin to the 5 volt power rail. So I'm now re-uploading the firmware with the correct port pin. Here. As the breadboard version only had one 3.3 volt switch GPIO, the firmware is not adapted to it, so I have to change it back and forth between the 3.3 and 5 volt rail. Yeah, that takes a while. So like this. Now it's nearly done compiling. And now it's uploading it to the board. I will just quickly measure a few different things, like the ground plane to be connected. Just to see if everything else is fine. But that looks all very good. So now we are back to this 3.3 volt rail in the working state. And if we now measure here, it has 3.3 exactly as it should have. The 5 volt rail should now be off, which is. And of course here, if we connect the ground and 3.3 volt, it should have everything as expected as well. Yeah, here we go. So also 3.3 volt. And now we also see the 1 volt line again. And if I connect to this again and to the glitch output, just to check it. And now we also have the correct voltage. So we can solder that in again. And after that, we can solder in another MOSFET, as it may seem like this is a broken one. which maybe also was the reason why it was a single one on that old module I used here to use. Yeah. Okay, so now if we connect again, oh yeah, that looks already better. So we have now the one voltage rail, 1 volt voltage rail, and the 3.3 voltage rail. And if I go to the glitcher and enable the glitcher, we should also be very, we should see the voltage drop I was talking about earlier. So it's now clearly visible that here the device boots. It first does its own initialization, and at this point it starts to read the log bit or the protection bit from the internal flash. So we can see the voltage drop where it draws a little bit more power than usual. And there we want to glitch at that exact moment. And yeah, I'm now going to resolder a different MOSFET in the hope that it then does work. So as this is the only thing left, that could be wrong. I will just quickly get another one. No, they are already here. So yeah, here we have a new module, and I will just desolder it like with the other one. So first pre-tinning the legs, and then tinning the main plate, however some would call it, and then retinning the legs to get all pins to a movable state, like so. So we now have the desoldered MOSFET somewhere under all this stuff. I am laying it back on the PCB and maybe just checking if there's anything wrong. Yeah, but it looks fine. So there again, just reflowing first the main, the heat sink. Yeah, that's really not the best work, but with all the camera gear in the way, it's not that simple. Normally it does look different. Okay, so maybe it works now. I will first connect the USB port, like so. We'll wait till the PC is connected again. You can add this also back to the stream. You can see it's running there again. I can just enable the glitcher, and also here we see a way better signal now. It's going into the minus voltage as it's trying so hard to get to ground level. So I will disable the glitcher again. I will reconnect the NRF. And first do an SWD init. See what it says. Okay, the NRF is connected but locked, which is okay. And then I will enable the glitcher. And we now should be able to see the exact same signal. What a damn stupid problem. Okay, maybe I should throw old pieces away. Okay, we can now see the 1 volt rail perfectly, the voltage drop, and here we can see the glitcher working and doing its ground level thing. It is now doing it at 2000 delay. This is very unscale. So it seems to be very good at scale. So we have a 2 milliseconds delay between the power on and the glitching itself. So it looks like we need to get it to 1000 or about 1000. So I will do the delay at 1000. And you can see it's clearly at the right position. And now I need to be fast to show it better. Like so. And we want to be at the exact point. So I need to do a little bit less, like 980. And yeah, it's still a bit too far. So I would now do 970, like so, and enable this again. And now it's the correct point. As we can see on some occasions, the voltage rail drop is not there anymore. This normally means it did work. The problem now is that the flash of the NRF is empty. So we definitely need to flash some firmware to it, which I will just do to show it better. Just need to think where I can get a better firmware now. I had a very nice Blink example, but this is a bit ago already. Some time. Yeah. I'm just looking for it. Yeah, these are the things you should save somewhere. This is now very annoying. I shouldn't have. Where do I get an NRF 52840 file? So I will just look for one pre-compiled example quickly. I am not showing it as it's maybe not the best way to do it. Browsing through all the files. So please stay tuned. And yeah, what are you doing today? What is your evening doing except for viewing this? Okay. Now I got one. A real file, a real dump. I just quickly need to get it onto the second PC. How do I do it? Okay, I got an idea. So I'm sorry for the annoying waiting, but I will be there. It shouldn't take too long anymore.
Yeah, this takes a while. I fully agree. Okay, I got one now. I now need to upload these files to the ESP32, and I will just name it A. A is the flash. This is a 1 megabyte file, so it will take a while to upload. And then the second one is UICR, that is a configuration registers, where also the log bit is set or saved. It's a 1 or 4 kilobyte area, which is used by the things. So as we are now in a locked state, and I cannot glitch it, as we saw in the oscilloscope and the ESP, I will just erase the complete NRF. And now we have it erased, and it is able to connect to it again. Of course, now it is fully empty, and normally this would good way, yeah. So now the echo should be away. Thanks, Patrick. Now the NRF is cleared, of course, and we could not be able to dump the firmware of it. That way it is prevented. So, but I will now flash the new file. I just uploaded and will upload it to 0 and flash the file. And we can now see that it is flashing it. As this is the 1 megabyte file, it does take a little. Let's just see if we can get myself on it. Yeah, like this. Maybe that's nicer to see. So we can now see it is, uploading it, and this is, as mentioned, taking a while, as it's a 1 megabyte file which is connected, transferred to a bit-banked SWD interface. And we will just wait till it's done. I'm just closing the window. So while this is flashing, I will just get a drink of water. Okay, so the phone is now screaming again as it's so hot. We will just let it cool down a bit to then reconnect it in a moment. So it was now fully flashed, and we can see it has a speed of around about 10 kilobytes the second. And we can also see now it's still connected. We can reinitialize the SWD interface, and we see the soft device is read correctly. It is correctly read that it is an NRF 52840. How much flash size it has, so 1 megabyte, how much flash size on the ESP is left, and how much it overall has. We now can still read these things as the log bit is not set. So if I will do it now, like this, we can see that the NRF is now locked, and it also read that the NRF is connected, but is locked. So if I now again do the initialization, you can see the SWD ID is read correctly, but it's just locked. So we now are in the correct state again to start the power glitching with the PCB. And I hope the phone is still too hot. I can sadly not turn it on right now. That's a bit unfortunate. So, oh, hi, B-Logic. So, that is very annoying now. It would be bad to not show it. Let me just try to get it a bit bigger. And maybe I can rotate the laptop camera just to the device to show it a bit better. Even if it's not the best quality then. Yeah, it should be doable. So we have this very messy place here. We have the ESP32 connected to the master board, where we then have connected the channel 1 of the oscilloscope to the trigger, and the channel 2 of the oscilloscope to the DEC1 power rail of the NRF. And if I now do, first I would reset the time to something different to see better what is happening. So like the 2000 again, like so we can start over like this. If we do the scaling a bit back, we can see clearly here the voltage drop of the glitching, and here in front we can see the voltage drop of the DEC1 voltage rail, where the flash chip, the internal flash chip of the NRF is red. If we now try again to find the right moment in time, I will just quickly do the 1 millisecond delay again, and we can see it is nearly at the right spot. I will just zoom in again, like here. And what we want to do is to go exactly at that point. So as we now know already from earlier that it is about 907 microseconds. And yeah, I will just click it, and we can see instant the NRF is stopping to be glitched. And if I now scroll down in the website, we can see here that the NRF is connected and the log bit is set. So it got a good power glitch. And yeah, as we can see, it was able to read the flash of the NRF again, even if the log bit is set. And this now all very compact and easy to achieve with thus just the target board. And yeah, basically, now we can do everything we would want to do, or we would be able to do in the normal unlocked mode. So we can read a register. So for example, here, The register 0 is this. This is the reset vector interrupt table, or no, only the interrupt table. If we read from address 4, like this, we can see it's A81. This is from the soft device, the reset interrupt entry point. Yeah, but that's not so important. What we would want to do is just to dump the full flash. So if I click it, it will again show here the ongoing flash dump. And if this is done, we could also dump the UICR. This is where some configurations are saved. And after that, we could then erase the NRF itself with this here button here on top. And that way we can reflash it with an unlocked firmware and or other firmwares. Just, yeah. To redo it, I will not wait till the dump is done now. I will just reset the ESP for now, just to show again how fast the procedure is. So let's just see if the connection is there again. This icon should blink again. Maybe I just refresh this side. It could also be that it doesn't need another reset, as it was in such a bad state at that moment. But here we go again. Yeah, we are back. So no task is running. The NRF should be still locked. So if I do an initialization, yeah, we can see it's still locked. We do know now we have a correct point at about 907. And just to show how fast it is. So I click it and yeah, now it's done. Now the glitch has worked. So we can now see it works fine. So what we now also can do is I will just repower the NRF so it is locked again. If I can get it right, like this. Still seems to be in the unlocked mode. Okay, now we have it correctly again. So I do an initialization. And now we can also use the ESP32 own glitching oscilloscope. In the beginning, I showed that the function or the graph did not work correctly, but now it looks better. If I can get it to full screen like this, so we can see a bit better how it would work there. We can see here in the beginning the voltage is quite high. This is the highest point and is about the 1.1 volt of the NRF DC1 rail. We then can see the voltage drop here, and here where it goes down to whatever where. This is where the glitch is happening. And we can see now we need to go further to the front. So if I now, for example, use the 1000, we can see it's still not at the right point. But we see how the delay is different and how we can that way get to the right point where we want to be. Then still, if you don't have an oscilloscope, you could just do a rough position like 100, and you would know, okay, it could be the right position. And you can then say here on the top, we want to go to 900, and the last is maybe 1100 microseconds. We set this and enable the glitcher. It will take a while since it is successful, as it starts at an earlier point. But here in the status, we can see it keeps increasing the delay and the width till it at some point is at the right point, maybe in 5 or 10 minutes, and it then is glitching correctly. And yeah, I think that's it for today. This broken MOSFET did cost a lot of time, but in the end we got it working, and I'm quite happy that the PCB works so well. So it's now possible to just use one of these master PCBs to prepare it, and then later to just connect the target boards to it, where then the wanted device is to dump the flash of it. Yeah. So again, this video is sponsored by PCBWay, and as you see, the quality is very good, and I'm really happy with them. So please visit their site, as you can get their PCBs for as low as $5 plus shipping at a very nice quality and speed if you take express shipping. This PCB will be part of the PCBWay PCB contest number 4. So if you could vote there, I will link it down in the description. Maybe it will get somewhere. Okay. I wish you all a good evening or morning, wherever you are. And now it's ready for bed. Thank you, Johnny. I'm also quite happy to be there. So it works. Okay, wish you all a great evening. I'm going offline now. Bye.